Hi everyone, my name is Deepak and I'm a graduate student at the University of Florida. This is my pattern recognition project. The topic of the project is speaker recognition using pitch and MFCC. Now, diving into the introduction, what is a speaker recognition system? Now, a speaker recognition system is used to identify the person from the characteristics of his or her voice. Now, the speaker recognition system can help us in a very big way by simplifying the task of translating speech that has been already trained and stored in a database. Now, it can also be used as a verification method, thus helping us with security processes. Now, this speaker recognition system can be divided into two parts. One is speaker identification and the other part is speaker verification. Now, in the speaker identification scenario, the speaker does not typically claim his identity, and it's the job of the classifier to determine the identity of the unknown speaker. But on the other hand, the speaker verification or authentication system is when the speaker claims to be of certain identity and the voice is used to verify this claim and to make sure that this person is not an imposter. Now, in a sense, we can look at speaker verification as a 1:1 matching, where the claim just has to be verified with one set of data, whereas speaker identity needs to be matched or trialed with all the data in the whole data set. Thus, the voice is being compared against multiple templates. Now, there are actually variants in a speaker recognition system as well, in which we can have either a text-dependent speaker recognition system or a text-independent speaker recognition system. Now, in text-dependent systems, the speaker is supposed to utter specific words or phrases which act like passwords in order to get access into a database or anything for that matter. But in independent systems, the speaker has the liberty to utter any phrase or words, because the speaker recognition system doesn't use actual words in order to identify the speaker. Practically speaking, the text independent speaker recognition system is tougher to implement, and since it has no words to play around with. Moving on to the applications, speaker recognition systems can be used in a variety of fields, where it can be used in banking, and there have been practical examples in which Barclays Bank in 2013 was to use passive speaker recognition to verify the identity of telephone customers within 30 seconds of their normal conversation. And there was also one more incident in February of 2016 where HSBC was about to offer 15 million customers its biometric banking software to access online and phone accounts using their fingerprint or voice. Now, this speaker recognition system could also be used in law enforcement activities, where a possible example could be in a jail, where the prisoner could actually use the speaker recognition system in order to identify himself and give a roll call sort of a thing, and where the person doesn't need to go for a roll call every day. And one more application would be in immigration services, where there has been a practical example between the countries of Canada and USA in the state of Michigan between 1996 and 1998, where the citizens of both the countries were given the permission to cross the border all around the clock, because the border wasn't open all the time, using speaker recognition system when they had nothing to declare to the customs office. Now, moving on to the existing approaches. Now, speaker recognition has been people have been doing research in order to crack this for the past 40 years, and there have been some very good algorithms that have been developed in this. So the first one is frequency estimation, and the goal of this method is to estimate the spectral density of a random signal from the sequence of time samples of the signal. So intuitively, the spectral density characterizes the frequency content of the signal. So this could be used for comparison in between voices, so that we could identify the speaker. And the second is there are many clustering algorithms as well, like KNN, which is going to be discussed in this paper. And there are hidden Markov models where the system is being assumed to be a Markov process with hidden states, and these Markov models can be represented as the simplest dynamic Bayesian network. So hidden Markov models were used for speaker recognition classifier. And the next one was using a Gaussian mixing model, which is a probabilistic model that assumes that all the data points are generated from a mixture of a finite number of Gaussian distributions with unknown parameters. Now these parameters of this GMM are estimated with the help of maximum likelihood, and the probability density function, that's the PDF, is assumed to take an arbitrary shape, and then the GMM probability density function can be usually represented using the covariance matrix, the mean vector, and a parameter set of mixture weights. Now moving on to the next one, that is neural nets and deep learning. Also they have been they were actually founded out in those concepts were introduced much later, after speaker recognition had been tried to crack down. So these are the new methods by which they are doing it. And then the last one is the vector quantization classifier, in which the process is where we take a feature vector of a large data set and we try to produce a smaller number of vectors, which in turn give us information about the centroid of the distribution. Now vector quantization works very well for if we have a very large data set, and because it usually gives you lossy data compression, but then usually the centroid gives us a good figure about the whole data set for each cluster. So these have been the existing approaches. Now moving on to our model, the model features that have been used in our project are pitch and Mel frequency cepstral coefficients. Now talking about the first feature, pitch. Usually pitch is defined as the degree of highness or lowness of a tone. Now when this pitch is being plotted against time, now this is called as a pitch contour, and it gives us an idea about the variation of pitch along the time. Now as you can see in that picture, it does vary a lot, and the pitch is also a unique characteristic of each voice. Now a person talking at us at one pitch might if a person is uttering some words in his voice, it might sound different, or at a higher pitch or a lower pitch, depending upon the person when it is being uttered by some other person. So it is actually a unique characteristic by which we could which could be used as a feature for extraction. Now the next one is Mel frequency cepstral coefficients. Now actually this could be would be called as MFCC. Now this MFCC is actually a representation of the short-term power spectrum on a non-linear Mel scale of frequency. Now these are actually derived from a type of cepstral representation of the audio clip, and these MFCCs are usually used as a feature for speech recognition or a speaker recognition, but they have been recently found useful in music information retrieval applications such as genre classification or audio similarity measures, which is also very similar to speaker or speech recognition. Now talking about the steps to compute this MFCC, first the signal needs to be framed, and usually the framing length is between 20 to 40 milliseconds. Now for in this project we have chosen it to be 30 milliseconds, which is the middle of 20 and 40. Now the next step is to take the Fourier transform of these frames, and then after that the next step would be to map these powers onto the Mel scale, so using triangular overlapping windows. And then while framing in the first step, we had used 75% of overlapping frames so that we don't miss out any information. And after this is done, we take the logarithm of the powers at the MEL frequencies, and then at the final step would be to do the discrete cosine transform of these MEL log powers. Now, the MFCs are actually the amplitudes of the resulting spectrum, and these are very good features to be used for speaker recognition. Now, moving on to the data and the classifier. The data is actually consists of 10 speakers with 13 recordings of each speaker, and then in order to use for training and testing, we have used 10 signals from 10 recordings from each speaker to train, and then 3 recordings from each speaker in order to test. Now, the classifier that has been used in this model is KNN classifier, and this classifier has been optimized using the hyperparameters. The hyperparameters that have been defined for the KNNs are the number of neighbors, and then the distance, which is Euclidean, and then the weights, which is normal standardized weights for the distances. So in order to evaluate these, the classifier or the recognition system, I have tried to calculate the confusion matrix, the validation accuracy, and confidence percentage for this purpose. Moving on to the evaluation process, this is the confusion matrix of the classifier. Now it can be seen that the diagonal gives you the values of true positives. Now it is considerably high when compared to the grid values in white color, because in white color because the data set has been classified pretty well, and the percentages which are there in the rightmost part of the picture and the bottom of the picture are just the normalized values for the percentages, and that's it. And moving on to the prediction and the confidence percentage. So this is the prediction that was done by the program on the test data sets that were given. Now you could be seen that it actually made 100% correct prediction, which is usually happens only when the data set is very small, like this. But then when the data set keeps getting higher, you could expect the prediction accuracy to come down a bit because of the large amount of data. Now, talking about confidence percentage is actually computed as the frequency of the prediction of the label divided by the total number of voice frames in the file. Now, for the validation accuracy, we had got a validation accuracy of 92.96%, which gives you a very good idea about how good the classifier is. Now, talking about the conclusions, we can see that the classifier gave us high accuracy, and then it gave us high validation accuracy as well. And this turns out to be a very good robust classifier, as adding some noise to it in the input wouldn't change the output, as these the voice signals are first pre-processed, and the voice frames are the ones that are being targeted in the whole signal. It's not the noise that we are targeting, hence it's a very robust system. Finally, I would say that this is a very good system, and with high accuracy, and since the accuracy is 100 right now, which is obviously only possible for a small data set, it will come down when the data set is larger. That is what I expect to happen. Anyway, thank you.